Ağlar güzel mi? Fizik yok.
So last time we looked on. Okay. Can I have everybody's attention, please? So last time we said you have a battery here, right? This is a battery, and this is the EMF of the battery. This is a resistor, R. And in what direction does the current flow? Clockwise. So the current will go clockwise. What would the current be in this case? Like this? Yes, that's correct. What's the power consumed or dissipated in the resistor? Okay, okay, like this. Okay, this is the power through the battery. And then the resistor, we can write it also as I squared R. And we can write it as like so. E is power, right? Energy per unit of time. Those are the units of power. Next, I would like to talk about resistors now in series and resistors in parallel. I don't think we started it last time, but my memory is kind of big. We did not start. Okay, let's do it. So, resistors in series. Resistors in series, they look like this. You got a battery, and then resistor 1, resistor 2, resistor 3, and you can have more. 3 are enough. Or 3. Okay. When the resistors are in series, they have the same current. The reason is, if you have a charge Q flowing, the same Q passes through this one, the same charge passes through this, the same charge passes through there. Just like if you have water in a pipe, it has to be the number of gallons per second passing, it has to be the same. In the same direction. Okay? So the current must all be the same, meaning that the current through resistor 1 is equal to the current through resistor 2, is equal to the current through resistor 3, and all of them are just called I. And the question is, if we were to replace all these resistors by the same, by one resistor, are equivalent, what would the resistance be? Assuming for the same voltage, you still have the same current. You still have the same current. Let's look at, we'll apply the loop rule. Okay. So, yeah.
So would it be the resistor with the least flow, or with the lowest resistance?
Will it be what?
The resistor with the lowest current flow?
Is R equivalent?
Yeah.
It will be related to all of them.
Okay.
Yeah, that's it. So we'll apply the loop rule. The loop rule says the change in potential over a closed loop is equal to 0. We will start here. What's the change in potential when we go from here to here? Positive E. And then we're going to cross this resistor in the direction of current. Current flows from high to low or low to high? It flows from low to high? High to low. Yeah. Just like water flows from high to low. It doesn't go this way, at least not by itself, right? Yeah. So current, to go in the direction of the current, the change is negative. So from high to low, so the change would be minus, and then minus what? Yeah, I1, R1. And then we will eventually get to it. And then next, from here to here, what's the change? Okay. And then from here to here? I3, R3. Is our loop complete? So must equal to 0. Okay? So we get E is equal to I1, R1 plus I2, I2, R2 plus I3, R3. Now look at this one here. What's the current in this one?
E over R.
E over R. Yeah. E minus I R equivalent is equal to 0. So yeah. So the current here, I is E over R equivalent, right? So E is equal to I minus R equivalent, right? That's E. So on the left side, I'm going to put I R equivalent. On here, I1 and I2 and I3, they're all I. That's right. So we conclude the equivalent resistance is just the sum of the individual resistors when they are in series. Yeah.
On a test, would we have to go through this whole through when we use that equipment?
Yeah, we can just go here. But we just have to justify it, and then we can just use it.
Okay.
Yes.
So you said that the flowing through R1 is smaller than, or assuming that like R1 has like a higher resistance, would you say it's smaller than the current flowing through R2 or R3?
No, it's the same current.
And what is the resistor resistance? Isn't it resisting the current?
So overall, if you have more resistance, you will have less current for all of them. Yeah. So, so the okay. Yeah. So if you have larger resistors, the current will be smaller. But the current through each of them has to still be the same. The number of charges per second passing through resistor 1 has to equal to the number of charges per second passing through resistor 2. And the same through resistor 3. There is no other path for them to go, right? Yeah. I'm not sure if it was this section. I didn't talk about this section. Okay. So it's similar to, I gave the example of cars passing through a tunnel. Yeah. If you have 10 cars coming in, you must have 10 cars coming out. So this is in series. It should remind you of capacitors in what connection? Yeah, parallel. Capacitors in parallel, you just added the capacitances. So resistors in series, they behave like capacitors in parallel. Okay. Next one, we're going to do resistors in parallel. And we're going to get another equation. Well, how do you think resistors in parallel would behave? Capacitors in series. How did capacitors in series behave? Yeah, you do reciprocals. Yeah, that's what we're going to get. So parallel, what did we call? Yeah, resistors in parallel. And the entire worksheet 10 is devoted to these, so I'm going to do little examples of this because the worksheet has a lot. So, resistors in parallel. Here's how they look like. You got your battery. You have a resistor 1, and then you have resistor 2, and you have resistor 3. Here's R1. This is R2. This is R3. This is your battery. Okay. Now, you have these junctions here, 4 of them. Now the current through resistor 1 does not have to be the same as the current through resistor 2, and it does not have to be the same as the current through resistor 3. Because, let's look at the total current. The battery will have charges coming this way, right? let's call the current here I. Okay? Current here I. So when this current gets to here, will all of it go this way, or all of it go this way, or some of it goes this way and some goes that way? Yeah, so some will go this way, and we're going to call that I1, because it's the current that will pass through R1. And some will go this way, okay? Some will go this way. Now this part, the one that goes this way, now, if you have I going in, I1 coming out, what would be here? I minus I1, good. Okay, so this I minus I1, when it gets to here, what does it do again? It's again. Some of it will go this way, and what do we name that? Yeah, I2. And then some of it will go this way, and eventually that will pass through here. What do we name this one? I3. Good. So now let's look at what happens on the other side. Let's look at what happens on the other side. You get I3. This is I3, right? So I3 and I2. So what comes out? Yes, I2 is going into this junction. I3 also is going into the junction. So what comes out is the sum of the two. That's the junction rule, right? The junction rule, remember what it says? The total current that goes in must equal to the total current that comes out. I2 plus I3. So now I2 plus I3 goes in. I1 is also going in, right? So what comes out? I, which is I1 plus I2 plus I3. Okay. So that means this total current, I, is equal to I1 plus I2 plus I3. So I and our goal is to find the equivalent resistance. Equivalent resistance. So meaning, if I were to replace these three resistors by just one equivalent resistor. And I would like to still have the same current, I. What should our equivalent be?
1 over I.
Yeah, let's look at, so I get I is equal to I1 plus I2 plus I3. Let's write everything in terms of voltages and resistances. What is I in terms of E and R equivalent?
Potential over
E over R equivalent, right? Is equal to I? I1 will be V1, the voltage across R1 over R1. Right? Because V is equal to IR. So I V over R. This is called Ohm's law, right? Ohm's law. So I'll apply it here. And then for I2, it's V2 over R2. And V3 over R3. Here. I'm just rewriting this. Now the top. What's the voltage across R1? It is E. The voltage across R2, V across R3. They're all E, they're all in the battery. Here's one way to think about that. I'll give you two ways to think about it. You can do the loop rule. You get E, right, minus V1 equals to 0. So E is equal to V1. Next one, you can do this loop. Start here, and then just do this loop that includes the battery and R2 only. So you get E minus V2 back to 0. E is V3. And then E minus V3 equals to 0. So E is equal to V3. Another way to look at it is this. You have two wires coming out of the battery, and the ends of the wires are touching R1. So R1 is experiencing the entire voltage. So V1 is equal to V. And then the same thing here. They're all experiencing all the voltage of the battery. So you can look at the loop rule or this one. Either way, you will get all of them. So E cancels.
That's the opposite.
Yeah, so resistors in parallel are like capacitors in series. So that's that. So next, I'm going to talk about charging and discharging of capacitors. That'll be my next topic. If there is time, I might do an example of this. If not, I will leave it for the groups.
So when it's resistors in series, the current going to all the resistors to when it's resistors in parallel, there are some areas where the current is less than the original.
If all these resistors were the same, if all of them are just R, and the current is I, a third of it will go through resistor 1, a third will go through resistor 2, and a third will go through resistor 3.
And then also, for the part that's above the I minus I1, yeah, so like the wire, that part, is that also I3, okay?
Yeah, it's the same branch, so it has to be the same current.
So I3 is equal to I minus I1. Minus I2 minus I3.
Yeah. Yep. So charging and discharging of capacitors. Okay. So here, remember we had batteries and capacitors alone. And here I have a battery with resistors alone. What if we have a battery and a resistor and a capacitor? What happens, right? And what happens is the capacitor would begin to charge. And in that case, how quickly is the capacitor going to charge? What's the charge as a function of time? So that's what I'm going to do. Can I erase this board? I'm going to write on the whiteboard here. Yeah.
So the voltages are equal when it's in parallel.
Yes.
Are they equal when it's in series?
No, they're not. The voltage across, so in series, V1 is I1 R1, and V2 is I2 R2, V3 is I3 R3. Yeah.
So for the board number E, you had I minus 1. Wouldn't that value also travel up, or do you only have I1 travel to right away to the other side, but they going to travel up where I2 was also flow?
This is I1.
But wouldn't it also flow up, or would not?
I1?
Yeah.
What do you mean, flow up? Like this way?
No, the other way.
This one?
Yeah.
I minus I1 is going up, yeah.
Oh, okay.
Yeah. And then it splits. Yeah. Okay. So I will write here, and then we will. So charging and then discharge. Okay. So charging RC circuit. And the reason it's called RC because there's an R and there's a C. So here is a battery. Here is a switch. Here is a resistor. Here is a capacitor. And then back to the battery. The capacitor is initially not charged. Okay? The capacitor is empty. It doesn't have any charge. It has zero charge, zero energy. Okay? And we're going to close the switch. Okay? We're going to close the switch. At t equal to 0, we're going to close the switch. And then we're going to ask what's going to happen. Okay? So at t equal to 0, we're going to close the switch. So I'm going to do that right now. Can I redraw this and just close the switch? So I'll just do it right here. So the switch will be closed. What happens? Current flows. Good. In what direction? Clockwise, right? So this is plus. So the current will go this way. Here is I. So the current flows. It gets to here. What happens? Plus charges are flowing. You start adding charge on the capacitor. So this plate will become plus, yeah, positive. And then here I have negative, right? And the current is going like that. So that's my loop. So the capacitor initially is not charged, and it's going to start to charge now. Okay, so let's do the loop rule. That's our friend. The loop rule is going to help us. So we're going to start here and ask what happens. So we go from here to here, across a battery. What's the change? Positive D. Good. Next, we cross a resistor and we're going in the direction of the current. So what's the change? Negative IR. Good. We're going to cross a capacitor from here to here. We're going from the plus end of the capacitor to the minus end. Is that a positive change or a negative change? Negative what? We call it VC. Okay, how about that? And then we come back and then see what VC is. This is the voltage across the capacitor. Circuit or the loop is complete, so equals to what? 0. So I have E minus. Current is the rate at which you're adding charge. It's what? dq dt. Current is dq dt. So I have R times dq dt minus, what's the voltage across the capacitor? If the charge is Q and Q over C. Yeah. Right, the definition of capacitance is C equals to Q over V. So V is Q over C. I want to get a function, I want to get this equation in terms of Q. So the battery's EMF or voltage is constant, the resistance is constant, the C is constant. Okay? So let me move dq dt. So I would have this. dq dt is equal to E over R minus 1 over R C times Q. Just moved and divided by R. Is this stuck there? Don't forget it. And divided by R. Our goal is to solve this equation. So what I'm going to do is I'm going to multiply here by C and divide by C. Okay, so everything has a constant. So I would have this. dq dt is equal to 1 over RC minus EC minus Q. So What kind of an equation is this? It's a differential equation, it's not an algebraic equation. But we can solve it by just direct integration. We don't have to do much. You separate the variable, you multiply both sides by dt, and then divide by this. So meaning, I'm going to have this. I would have dq divided by dc minus q equal to 1 over rc times. Okay? So now, the next step is to integrate. Let's integrate. This is constant, so integral will go, we close the switch at equal to 0, so the initial time is 0, and we want to know the charge when time t has passed. T. What was the initial charge of the capacitor? At equal to 0, what was the charge? Yes, it was not charged. And then later on, it's going to be some charge q. We're going to call it little q. Okay. What's this integral?
Negative principal.
Okay, I heard ln of EC minus Q, but you have to put a minus sign, right? Because the chain rule will give you a minus. Good. Evaluate it between 0 and Q, right? Equals to, for this one, it's just 1 over RC times T. When T is equal to T, it's T, and then at 0, it's 0. And now I need to just evaluate, right? I'm going to, I will move this minus sign to the right side, so I have minus T over RC. And then here I have, ln of minus and then this becomes the ratio, right? Multiply both sides by this. I want to solve for Q. I want to have Q on one side, everything else on the other side. So I get move Q to one side and these to the other side and factor the BC, so you get Q C minus 1 minus E minus over R C. That's it. Then I'll just also write I. I is dq dt, right? Take the derivative of this. Derivative of 1 is 0. Derivative of e to the minus t over rc would be minus 1 over rc times this. But I have a minus sign becomes plus. C on the bottom, C on top cancels, so you just get e over r, right? Yeah.
Shouldn't it be negative EC after you take the EC to the other side? EC minus Q?
No.
Oh.
Yeah, it would.
Okay.
You can double check.
Because the Q is negative.
So this is for charging a capacitor, right? So let's graph the charge versus time. here is time, and here is the charge. Let's plug in 0 for t. What do we get? What's e to the 0? 1. 1 minus 1 is 0. So the charge is 0, right, initially? Which is expected, right? The equation should give us what we already know. As t goes to infinity, e to the minus infinity is 0. So you just get 1 minus 0 is 1. So you just get EC. So as time goes on, the capacitor will charge up to EC. You can't get beyond that. So that's all. That's the total charge. Notice also, if the resistance is really high, will the capacitor charge slowly or fast? Should be slow. If the resistance is high. Let's look at the opposite. If the resistance is really small, if the resistance is tiny, how long will it take the capacitor to charge? It would be quick, right? You expect it to be quick. How quick? Let's say if the resistance is 0. You will have something minus 0 that's infinity, right? So e to the minus infinity is 0, so it will just take 0 time basically to charge. So less resistance, the capacitor will charge quickly. Large resistance, the capacitor will charge slowly. So the resistor controls how fast the capacitor charges. That's why when we just had the battery with the capacitor, if someone asked me, how long will you have a current? If it's truly 0 resistance, you will just have current for 0 time. Just close to 0. And when you have a resistance, it's realistic. You will have some resistance always. It will charge quickly, but not at within 0 time. How about the current? Here is the current as a function of time. Here is the time. Here is I. What's the current at t equal to 0? Just E over R. It's E over R. At t equal to 0, the current is E over R. Right? E to the 0 is 1. How about as t goes to infinity, what would the current be? When t approaches infinity, the current will approach 0. Right? It decays, right? E to the minus infinity is 0, so you just get 0. So that makes sense. As the capacitor charges, the capacitor gets more and more charged, the current would become less and less. Right? Because if the current stays the same, it means you keep piling up charge indefinitely, and you will have a lot of charge. But the limit is the current will when the capacitor has the same voltage as the battery, the current will stop flowing. Basically, the battery is trying to pump charges this way, and the capacitor will be resisting them that way with the same force. So it will stop charging. That's what this equation. It depends. It really depends if you want to. Yeah. Sometimes, let's say if I want to discharge a capacitor really quickly, we will talk about discharge. I want really high resistance to be discharged quick. And if I want to, I'm sorry, I want very low resistance to be discharged very quickly. So it's just how quickly I want things to go. So from an applications point of view, it depends on what you want.
No more battery will still have
Oh, yeah. And when does that happen? When does the current stop Yeah, and how long does it take for the capacitor to be full? According to these equations. Infinite amount of time. That's the horizontal asymptote here, right? It will take infinity for the current to go to zero. Right? But here's the current. What is this zero? When t approaches infinity. So, the next one, yeah.
In what case would you want more resistance, in what case would you want less?
Depends on the application. I am not an application.
Yeah.
Yeah, so ask an engineer, I would say. It really does depend on what you want to accomplish. So for now, there is not much to this, right? We would have, there are different applications for circuits. When you have more other components, there are definitely applications. I want to talk about discharging. But now you have charged it, and then the question is, how does it look like when I want to discharge it? And that's the last topic in this chapter. And then, did you have a question?
No, I think I know the answer when we do discharging.
Okay, let's do discharging. Okay. So here is the discharging. Oh, let's name it discharging, right? Discharging a capacitor. Okay? So to discharge it, you must start with it charged, right? So the capacitor has been charged. So here is the capacitor. And here is the switch. Here is the resistor. Capacitor is fully charged, has lots of charges here. Let's say it's Q naught, right? Initially, the charge on the capacitor is Q initial. I don't know how much it is, some initial number, okay? Oh, this is C, this is I. And that's a switch. And we're going to close the switch. So we're going to close this switch and then ask what happens. And then our goal is to find an equation for the charge as a function of time. Can I close the switch? All right, so let's close it. Oh, actually, when the switch is open, how much is the current? Yeah, yeah. Now you close the switch, and the question is, in what direction will the charges start to flow? The current will go clockwise, okay? So the current will be this way, right? I. This is the current. So what happens to the charge on the positive plate? It becomes less or more? Yeah, it will start losing. Current is the direction of plus charges. So plus charges are